This is how to solve a polarity problem. First, let's look at what the question is asking us, which is how many of these molecules are polar. We have 4 simple steps for solving this problem. First, we should draw the Lewis structure, then calculate the electronegativities and draw the bond dipoles, identify partial charges, and identify the net molecular dipole. Let's begin to solve the problem for each molecule one by one. We can do this correctly by using the rules we learned about Lewis structures. The first molecule we will look at is SO3. It has 24 valence electrons. So to draw the Lewis structure, we started by placing the valence electrons on the outside atoms first. We had used all 24 electrons, but the S atom did not have a full octet, so we had to make a double bond between one of the O's and the S central atom. Now let's look at the bond dipole. The highest electronegative atom, which is O, will have partial negative charges because the electrons drift towards the atom with the highest electronegativity. That means there will be a partial positive charge on the S atom. The bond dipoles are going to look like this. A tail that's positive on the S heads towards the O on the outside. The arrows show you the direction of the charge separation, and the length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the 3 domains around the central atom. 3 domains is a trigonal planar molecular geometry. Since all of our domains are the same, we will have no net dipole, meaning that this molecule is nonpolar. Next, we will look at OF2 to see if it is polar. There is a total of 20 valence electrons, so we drew the Lewis structure the same way we did the last one by putting the valence electrons on the outside atoms first, and we were able to get all the valence electrons on the atoms, with each atom having an octet. Now let's look at the bond dipole. The highest electronegative atom, which is F, will have partial negative charges because the electrons drift towards the atom with the highest electronegativity. This means there will be a partial positive charge on the O atom. The bond dipoles are going to look like this. In order to find out whether the bond dipoles cancel or not, we have to look at the 4 domains around the center atom. Since there are 4 domains and 2 of the domains are lone pairs and 2 of the domains are bonds, OF2 has a bent molecular geometry. We have an F and 2 O's on the outside, so the dipoles go from the O down to the F. Because of the molecular geometry, the net dipole will be going down. The dipoles in the bond don't cancel because of the molecular geometry being bent. There is a net dipole in this molecule, so it is polar. Now we will look at BeCl2 to see if it is polar. There is a total of 16 valence electrons. We have used all 16 electrons, but the central atom Be does not have an octet. This is okay because Be is an exception to the octet rule. Now let's look at the bond dipole. The highest electronegative atom, Cl, will have partial negative charges, and the Be will have a partial positive charge. In order to find out whether the bond dipoles cancel or not, we have to look at the 2 domains around the center atom. Since there are 2 domains on the central atom, the molecular geometry is linear. Since all of the domains are the same, there is no net dipole, making this molecule nonpolar. Now we will look to see if CCl4 is polar or nonpolar. There is a total of 32 valence electrons, and we have used all 32 electrons, and the central atom also has an octet. Now let's look at the bond dipole. The highest electronegative atom, which is Cl, will have partial negative charges. That means that the C atom will have a partial positive charge. There will be 3 other dipoles going this way, this way, this way, and this way, all towards the Cl because that has the partial negative charge. And in order to find out whether the bond dipoles cancel or not, we have to look at the 4 domains around the center atom. 4 domains is a tetrahedral molecular geometry. Since all of our domains are the same, we will have no net dipole, which means that this molecule is nonpolar. Lastly, we will look at O3 to see if it is polar or nonpolar. There is a total of 18 valent electrons. We have used all 18 electrons, but the central atom O does not have an octet, so we will have to make a double bond with one of the outside O's and the central atom. For this specific molecule, we will not look at the bond dipoles because all of the atoms have the same electronegativity. Since there are 3 domains and one of the domains are lone pairs and 2 of the domains are bonds, O3 has a bent molecular geometry. Because of the molecular geometry, the net dipole will be going down. The dipoles in the bond don't cancel because of the molecular geometry being bent, so this molecule is polar. So let's look at the problem, which was asking us which of these molecules is polar, and we found that 2 of them were. These 2 molecules are polar because their domains were not all the same, and these 3 molecules are nonpolar because there was a net dipole because their domains were all the same. Some common mistakes that take place when solving these types of problems are people sometimes draw the Lewis structure wrong because they may have counted the number of valent electrons incorrectly. Oftentimes, people forget the exceptions to the octet rule, which could lead to putting the wrong number of valent electrons around the center atom. People could also forget about non-bonding electrons or not know the geometry, which would make it harder for them to figure out if the dipoles cancel or not.